Mr. B.ThanaSekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharathidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series. In this series, we are having the subject that is theory of computation. This is going to be the fourth episode of theory of computation subject. Let's start with the recap of what we had in the previous lecture. In the previous lecture, we have seen that is how deterministic finite automata and non-deterministic finite automata, that is in general how the finite automata were represented. We have seen three methods. One is the formal representation using the quintuple with 5 components of the finite automata, and the other one is the transition table, and another one is going to be the transition diagram. Transition table is the tabular representation of the finite automata, and the transition diagram is the graphical representation for the finite automata. After that, we have seen some examples for which some languages will be given for you, and from that we will be constructing the deterministic finite automata. So, we did not see any kind of algorithm for the transformation of the language specification into its equivalent deterministic finite automata. Straight away, just by seeing what is going to be the language and how the automata is derived, we will be finding the deterministic finite automata. And the next component we had seen in the previous lecture is the definition for the non-deterministic finite automata. That means that is and as far as DFA is concerned, the resulting states can be at most 1, but whereas in the case of non-deterministic finite automata, the resulting states can be, that is, more than once. That means the system can be in more than one state at a time, and the reason why we are going for that NFA is just because of the easiness available in the construction of the finite automata. So, directly coming up with deterministic finite automata is difficult than when you are talking about the construction of NFA. So, in this episode we are having how the strings are all processed by the NFA, and there will be some kind of equivalence, that is, as far as the language recognition power of both NFA and DFA are concerned, they are equal. So, we should prove that the equivalence of the language recognition of NFA and the language recognition of the DFA. So, given an NFA, we should be able to transform into its equivalent deterministic finite automata, subject to the condition that the language recognized by the DFA, which is derived from the language that is given NFA, should be same. So, then only we can say that the language recognition power of both NFA and DFA are going to be same. Let us start with the language recognized by the NFA first of all. So, here is the definition. So, the language recognized by N, that is N means the non-deterministic finite automata, is a set of all strings X, and the condition here is we have the extended transition function for the NFA, that is going to be del cap of Q naught, where Q naught is the starting state of the given non-deterministic finite automata, and X is a string which we want to verify whether it is there in the language or not. So, we are finding del cap of Q naught comma X. So, we will get one or more number of states as output. It is because of it is NFA, it is not necessary that we should get always a single state as output, we may have even more than one state as output. To find whether this X is accepted by this finite automata, that is NFA, we have to find out whether there is any common state in between this expression and this set, that is F. F is actually the set of all final states or accepting states. Even if you find at least one state common to these two expressions or these two sets, then we can say that the string X is accepted. So, that is how related by this expression. So, del cap of Q naught comma X intersection F, if it is non-empty, then we can say that X belongs to the language of this NFA, and the condition here is X must be derived only from the alphabet, that is sigma star, that is a closure of the given alphabet. And the string it is accepted if there is a path from the start state to any one of the accepting state. As far as deterministic finite automata are concerned, it is going to be a path to one accepting state, and here we may have, that is, any number of states we will reach at the end because of the transition function definition, it is going to be 2 power q, not exactly q. So, but the condition here is from the resulting set, even if you find at least one state from this EF, then we can say that this string x is accepted. So, this is how we are defining the language of any non-deterministic finite automata. So, now we have to find out how we are recognizing the strings with the help of the transition function for the non-deterministic finite automata. I already used that del cap as the function, that is the extended transition function for the recognition of the strings. The difference in between the extended transition function and the conventional one del is the input, that is second input. Both of them are accepting one input as that is a first state, that is a state of given state, and then the second input is going to be the set of states, that is your sequence of symbols, that is going to be the string. If it is del, we will accept one symbol. If it is going to be del cap, we will accept a set of the sequence of symbols, that is going to be the string. Now we shall see that is how we are defining the extended transition function for the non-deterministic finite automata. We have already seen the extended transition function for the deterministic finite automata. It is del cap of some q comma w. How this w, there is a string, is going to be accepted by the finite automata. So, we will be having a recursive definition for that. We will divide that w into xa. First we will evaluate the transition for x, then we will apply the transition function for a. Finally, whatever we are getting is going to be the resulting state after accepting all the symbols available in the given string. Here also we have a similar kind of definition. Since it is going to be a recursive definition, the first step is going to be the basis. So, what will happen as far as the empty string is concerned? So, del cap of q comma epsilon is going to be q. It is same as the transition function, that is extended transition function for a deterministic finite automata, because if you find that nothing is given as input, that means empty string, then you can't change the state. But we have a variant of NFA, that is epsilon NFA, where we will find that epsilon can also make some kind of changes on the state. But as far as DFA and the NFA are concerned, it is not possible to change the state without accepting symbols. So, that is what we are having del cap of q comma epsilon is going to be q, that is no input and no change of state. So, now we shall see that is how it is inductively defined, that is this function is inductively defined, and w is a string, we are assuming that is given, and we have to verify whether it is going to be accepted or not, or assume that we need to find out the resulting state after accepting all the symbols available in w. We have a division for the w, or we are seeing the w as a split of, that is x comma a, that is xa, where x is once again belonging to sigma star and a belongs to sigma. It means that a is a single symbol and x is any sequence of symbols from sigma. And now the question is, how do you find out the transition for this w from the given state, that is q? So, here we are saying that first we are evaluating the transition for x, that is del cap of q comma x we are finding. Since it is going to be a non-deterministic finite automata, we will get a set of states as resulting states. If it is deterministic one, we will get either q or p or c, some single state will be available as output. Here it is going to be a non-deterministic finite automata, so definitely we will get one or more number of states. Actually, it is going to be the subset of power set of the given set of state, that is capital Q. So, we are assuming that del cap, that is after applying all the symbols from this given, that is string, that is w, that is from this x, for the state that is q, we are getting the resulting state, that is p1, p2 up to pk. So, now what we have to do in addition with whatever we have got is applying the transition for a. A is going to be a single symbol. So, we can straight away go and apply the transition for a using the transition function del rather than going for del cap. So, del cap here it is recursively defined, and now in order to find out the transition for a, which is the remaining symbol available in w, what should be done is consider the transitions from every state, that is p1 to pk. So, that is what we are doing here, del of p I comma a for all I varies from 1 to k. That is, we need to evaluate the transitions from every state, that is pi, for the same symbol, that is going to be a. So, what we will get as output, once again because of this transition function is also a transition function from non-deterministic finite automata, we will be getting a set of states as output. What those set of states? It is going to be R1, R2, R3 etc. up to Rm. We will get another m number of states as output. So now we have to just combine these two steps in order to evaluate the transition for del cap of q comma w. W is actually divided into two components, one is x and one is a, and x is a string for which we are evaluating transition initially. After that we are getting p1, p2 up to pk. Then from these set of states, that is we are evaluating the transition for a. So the resulting states are r1, r2 up to rm. So ultimately what we will get is del cap of q comma w is going to be r1, r2, r3 etc. up to rm. So you can see that everywhere we are getting set of states p1 to pk, and here it is r1 to rm. It is only because of it's going to be a transition function available in the non-deterministic finite automata. So the difference in between the transition functions of the NFA and DFA are only in terms of the resulting states. DFA means there will be only one state as output, and NFA means there will be a set of states we will get as output. We shall see one simple example in which how we are evaluating the transition, that is transition function, that is extended transition function for some string that is x or y. Here is the example. The automata is available here. Actually it is the automata going to recognize any set of strings terminated with 0, 1, and it is NFA because of we have two transitions for 0 from q0. So you can either go to q1 or you can even come back to that is q0. Because of these transitions, this is going to be a non-deterministic finite automata. Now we go to verify whether the string 101 is going to be accepted by this finite automata or not. So this will actually accept any string terminated with 01. So since 101 is also terminated by 01, we can say that this string 101 is also going to be accepted by this finite automata. But we have to verify that. At the end, if you are able to get a subset of states from the set of states of this automata in which q2 is a member, then we can accept that 101 is going to be accepted. So that is what we have to verify now. We start with q0, that is going to be the starting state of the given non-deterministic finite automata. The string to be verified is 101, and it is to be divided into xa. What the x here is, that is 10, and a is nothing but 1. So for this x, you just once again applying del cap. So del cap of q0 comma this 10 comma del of it is 1, and this is once again going to be recursively expanded by using the same rule. It's del cap of q0 comma 1, that is your x, and what remains is going to be a, that is a is nothing but 0 here. The same story once again, we will be having del cap of q0 comma epsilon, and because of x is an empty string and a is going to be 1. So now we have reached the base condition for the transition function. So what the basis says is del cap of q0 comma epsilon is going to be q0. That is for any state, if the given input is going to be epsilon and it cannot make any change on the state, that is current state. So del cap of q0 comma epsilon is going to be q0. So that is what here we are having. And now we have to keep on apply the transition function del for all the symbols available in the that is string. First it is for 1, we evaluate the resulting state, then it is 0, evaluate the resulting state, then 1, we have to evaluate the resulting state, that is going to be so. So if you are doing so, you see that is q0 1, it is actually going to q0 because of this transition, and then we are having that is q0 comma 0. So for that we will get two number of states, it is going to be q0 and q1, and finally we have only one symbol, that is 1. So for that we need to evaluate transitions from both q0 and q1. So from q0 for 1 we are coming back to q0, and from q1 for 1 we are going to q2. So finally we are having that is q0 comma q2, and we have to check whether there is any final state available in this set or not. We have a final state, that is nothing but q2, so we can say that the string that is 101 is accepted. So the condition is you apply the transition function, that is extended transition function, and evaluate the transition from all the states available in the subset produced by the various transitions, and finally you check whether we are able to get at least one final state or not. If so, the string will be accepted. If not, we can simply reject this string as not accepted. Let us go for a small break. After that the lecture will continue. Welcome back. So before the break we have seen that is how the transition function, that is extended transition function, is used for recognizing strings by the non-deterministic finite automata. So now we have the definition for NFA, definition for DFA, the extended transition function for NFA, extended transition function for DFA. So with all these things, we will be able to know how we are defining languages of these finite automata, whether it is going to be a DFA or it is going to be an NFA. The very important point here we have to remember is the language recognition power of both NFA and DFA are going to be same. So if they are all same, then given an NFA, you should be able to transform it into DFA. Similarly, the reverse, a DFA can be considered as an NFA also. So DFA, every DFA can be considered as an NFA because it is not going to be a mistake. See, the condition for an NFA is resulting set of states can be even have one or more number of states. As far as DFA is concerned, always we will get one state as output, so that can even be considered as NFA also. So there is actually equivalence available in between NFA and DFA, but the difference here is maybe the number of states and the transition function. As far as NFA is concerned, we will have more number of states as output, but DFA means we will be having a single state. Since there is an equivalence available, we should learn that is how we are transforming the given NFA into its equivalent deterministic finite automata. So here we have an algorithm actually that will give you the how the NFA is transformed into deterministic finite automata. The conversion from NFA to DFA is mandatory because NFA has lot of non-determinism, which we will find very difficult when you are writing programs or when you are designing the actual tools. But whereas deterministic means, DFA means there is no non-determinism, so you can very easily go for transforming them into programs which can be very easily transformed into some executables so that we will have the valid recognizers. So here is the conversion, that is how we are going for the equivalence of NFA and DFA. So the first thing is we should understand that every language that can be described by an NFA n can also be described by some DFA d, subject to the condition that L of n is same as L of d, that is the language of both must be same. But when you go for the conversion from the NFA to the deterministic finite automata, we should think about the complexity, that is the complexity in terms of the number of states. So the DFA equivalent of an NFA with n states will have 2 power n states. It is the reason because of you can think about that there is a DFA given for you which is having 3 number of states. The transition function for the DFA says that is q cross sigma will give you q, but whereas the equivalent deterministic NFA, the transition function is q cross sigma is giving you 2 power q. That means the resulting state can be any one of the subset of the power set of q. So now we have to understand what is going to be the number of subsets available in the power set of q. It is fully depending upon how many states available in q. If there are n states available, then we will be having 2 power n number of states as the member of the power set. So you may get any one of the states. So we need to consider all possible states that can be derived or that can be obtained from the NFA for the equivalent deterministic finite automata. So at the most we will be having 2 power n number of states. That is actually the worst case behavior. But in the best case, if you are given an NFA with n number of states, we will get only n number of states in the equivalent deterministic finite automata. So that may happen, suppose if the given NFA itself is having determinism on all respect, that is with respect to all these states, so we will be able to consider the same as the deterministic finite automata. In that case, the number of states will not increase. But most of the time, the possibility of generating all the 2 power n states is going to be a very rare event. Only in a very specific case we will be able to generate all the, or we will be getting all the 2 power n number of states. But always the deterministic finite automata equivalent for the given NFA will have most of the time more number of states than the number of states available in the given NFA. The next is the input alphabet. We have seen that the language recognized by both NFA and DFA are going to be same. So if they are going to be same, then there should not be any change as far as the input alphabet is concerned. So the alphabet for the given NFA should be same as the alphabet for the deterministic finite automata, then only there will be equivalences. If you are allowed to have changes on the alphabet for the NFA and DFA, the language generated by both the finite automata will be different. And now the question is, what is the algorithm used for the transformation from the NFA to DFA? Actually it is, since it is going to be the construction of all the subsets available in the power set of Q, we are having the name called that is subset construction. So the name of the algorithm used for converting the given NFA into its equivalent DFA is called the subset construction algorithm. So here is the algorithm available. We are given with the n, that is non-deterministic finite automata. which is having all the 5 components of any finite automata, that is Qn, sigma, del n, Q naught and Fn. So now we have defined what is the equivalent deterministic finite automata for the same NFA. It is named as D, and initially we have generated all the components and we have to learn how these components are generated one by one. We will be having set of states, that is QD, and you can see that as far as sigma is concerned, it is not differentiated from the NFA sigma and the DFA sigma. It is only because of the condition that the alphabet for both the automata must be same in order to retain that the language recognition power is going to be same, or the same language is to be generated by the equivalent DFA also. But whereas in our looking at the third component, we are having a different transition function del D, which is not same as del n. So this del D must be derived in terms of this del n. And the fourth component is the starting state of the deterministic finite automata. There is only one starting state available in the given NFA, and the same state is going to be used as starting state for the deterministic finite automata also. The reason why we are having it inside the set bracket is, as far as the DFA states obtained from this NFA are concerned, they are all the subsets of the power set of this Qn. So Q naught is also going to be a subset of the power set of this Qn. So we are using the representation that every state available in the deterministic finite automata equivalent for this n must be written inside the subset, that is set bracket. And finally we have to study what is going to be the final states of the deterministic finite automata. Let us start with how this QD is obtained. So QD is the set of subset of this Qn. Q1 is the NFA states. Suppose if you are having 3 states like your Q0, Q1, Q2, then we will be having Q0, Q1, Q2, then Q0, Q1, then Q0, Q2, then Q1, Q2, and finally it is going to be Q0, Q1 and Q2. These are all the possible states. But do we get all the states or not is fully depending upon what kind of problem we are given with and how it is transformed into deterministic finite automata. So QD is the set of subset, that is condition here is S must be a subset of Qn, and how many number of states we will be having in that QD, that is the order of this QD. It is going to be 2 power the number of states available in Qn. If you are given it an NFA with 3 number of states, then in this QD we will be having at most 8 number of states. And another thing we have to remember is all the states in QD may not be useful for us. It is once again problem dependent. The remaining components, you can see what is going to be the start state. The start state already I talked about that. It is we are having only one state as the start state as far as the NFA is concerned, and that state you have just put it inside the set bracket and we will get the start state of the given deterministic finite automata, the resulting deterministic finite automata. And what we will be getting as the final states. The final states is the set of all subsets from, that is Qn. What is the condition? You find the set of all subsets such that at least there is one member from Fn. Fn is the set of all final states of the given NFA. So if there is a common state in between Fn and any S, then that S is going to be treated as a final state of the deterministic finite automata. As an example, suppose Q0, Q1, Q2 are the 3 states available in the given NFA with the Q2 as the final state, then Q0, Q2 is a final state. Q0, Q1, Q2 is also a final state. Q2 itself is a final state. Once again, whether it will be really used in our finite automata or not is fully depending upon the problem. So the set of all final states are obtained by the set of all subsets S such that there is a common state in between S and Fn, then S will be in the set of all final states. So now the only component remaining for the conversion is how we are evaluating the transition function del D from the transition function for the given finite automata, that is non-deterministic finite automata. As far as del D is concerned, its first component, that is the state, is a subset of this Qn. So this is not going to be a single state of NFA, it is considered as a single state of DFA, but it is having a set of states from the NFA. So now to evaluate the transition for A from this S, we need to evaluate the transition from every state of this S from the transition function for del n. So suppose we are having, that is the relation, that is the union of, for all P in capital S, we evaluate the transition P comma A using the transition function given for the non-deterministic finite automata. So del n of P comma A for all P in S, we just take the union of everything. So what we will get is another set of states as output. So we are passing a set of states as the input, and we will be passing one symbol as the second input of this transition function del D, and we will get another set of states as output. So we have to do this for every state available in QD, so we will be able to have all the, that is, transitions for this del D. So this is how we are defining the transition function for the, that is, deterministic finite automata equivalent. The explanation is, take the union of all the states of Qn which can be reached from each P in S for the input, that is A in sigma. So this is what the algorithm that is given for the conversion from deterministic non-deterministic finite automata to the deterministic finite automata. It's named as subset construction algorithm only because of the DFA for the equivalent NFA is going to be evaluated by constructing the subset of the states of the given NFA. Here we have a simple example for that. So this is an automata in which we will be having the non-determinism from the 0, that is Q0 for 0. So Q0 0 is going to Q1 as well as coming back to Q0. So here is the non-determinism available. And other than that, we are having Q0 here, it is non-deterministic, Q2 is non-deterministic, and we have some of the states for which the transitions are all not at all defined, that they are all denoted by pi. To convert this into its equivalent deterministic finite automata, so first we have to start with the starting state of that is your given DFA, NFA, that is Q0, that is starting state, and now we have to apply the transition 0, and then we have to apply the transition for 1. By the algorithm, what should be done for the evaluation of the transition for 0 is, that is, we will just go to the transition diagram or transition table. Q0 comma 0 is Q0 and Q1. So we are getting Q0 and Q1. Then for 1 it is going to be Q0. So we are just copying, that is Q0 here. So now we have to find out, there are two ways to, that is, continue further. Either we can generate all the subsets of the power set of, that is Q, that is one of the case. Otherwise we can just proceed with what are all the states which are newly generated for every transition. Here we find that we are generating two new states, not two exactly, it is going to be one. One is Q0 Q1 and one is Q0 which is already evaluated. So we can evaluate the transitions for Q0 and Q1. But what I have done here is, we have generated the subset of all the, that is, states of this Q0 Q1 Q2. So in the order Q0 Q1 Q2, then Q0 Q1, Q0 Q2, Q1 Q2, Q0 Q1 and Q2. So we have generated the transitions for all the states, but whatever the states which are colored in green, they are all the useful states. The states which are colored in blue are the useless states, because there is no possibility of reaching these states from the starting state of your finite automata. So those states are not doing anything useful as far as the language recognition of the finite automata is concerned. So here we find Q0 Q1 is labeled in green, so it is doing some useful job in terms of the language recognition. So we are coming for Q0 Q1, and the transition for 0, we have to evaluate from Q0 for 0, it is Q0 Q1, and then it is for Q1, and from Q1 for 0 no transition available. So once again we will get back, that is Q0 Q1, but whereas in the case of 1, if it is from Q0 we will get, that is Q0 as output, and if it is from Q1 for 1 we will get Q2 as output. So it is going to be Q0 and then Q2. We find another new state is generated, that is Q0 Q2 is the new state. Evaluate transition from Q0 Q2. From Q0 and Q2 for 0 we will get once again Q0 comma Q1 as output, and for 1 we will get only one state, that is going to be Q0. So that is from Q0 we are getting, that is Q1, that is Q0 as output. So now we have, that is, generated almost all the states required for the equivalent deterministic finite automata. Remaining states are also available. If you are taking any, that is, flow from the starting state, you can either go to Q0 Q1 or Q0. Q0 means we are coming by the same state. If it is Q0 Q1 we will come here. From here we can either go back to Q0 Q1 or you can go to Q0 Q2. For Q0 Q2 also the transitions are all evaluated. This is state already we have, for which these transitions are evaluated. For this also we have already generated all the transitions. So what we need to understand here is, the remaining states are not having any useful job as far as the transition function is concerned. The starting state is Q0, and there is a final state is going to be the member in which final state of the given NFA is a member. So it is going to be Q0 and Q2. So we will be having the transitions for the deterministic finite automata. So this is how we are transforming the NFA into its equivalent deterministic finite automata. Here is the transition diagram which is equivalent for the DFA. So let us go for the summary of this lecture. We have started with the language recognition of the NFA with the help of the definition for the non-deterministic functions extended transition function, non-deterministic finite automata's extended transition function. And then we have seen that is the equivalence of the deterministic finite automata and the non-deterministic finite automata. After that, we have seen the language, that is conversion from the NFA to its equivalent DFA with the help of the subset construction algorithm. We have seen the subset construction algorithm also. One example also we have seen. And then we can, if you are looking at the question, possible questions here. So one is the definition for the extended transition function of NFA. It is slightly differing from the definition for the extended transition function of DFA. So that may be a possible question here. And another important question is the construction of that is subset construction algorithm. Actually, it is used for transforming the NFA into its equivalent deterministic finite automata. And another question which we will be facing is in terms of the complexity of the conversion process. When you are looking at the complexity, means it is actually the number of states we will get as output from the NFA to the deterministic finite automata. Already I talked about that. It is n number of states in the NFA, means we will be having 2 power n at most, a minimum of n number of states and a maximum of 2 power n number of states we will get as output. That is once again fully depending upon the problem context. These are all the possible questions. We may have plenty of problems for the conversion from NFA to DFA. So whatever be the case, we are having the algorithm, that is subset construction algorithm. Just apply that, we will be able to get the deterministic finite automata from the NFA. Just a cross check, we can verify with a few strings. You take a string from the given NFA and you check whether the same string is going to be accepted by the DFA or not, and similarly take a string which is not accepted by the NFA and check whether the string is going to be accepted or not. It should not be accepted, then only we can say that the language recognition power of both NFA and DFA are going to be same. So with this I conclude this lecture. Thank you all.